Okay, Assalamualaikum warahmatullahi wabarakatuh, and a very good morning. So, because we don't have face-to-face class today, so let's just do it via video. So, this is our new topic. It is molecular diffusion in liquid. So, there are several contents here. So, we'll start with accumular counter diffusion and diffusion of A through non-diffusing B, and then we have diffusion coefficients and prediction of diffusivity in liquids. Let's start. So first thing first is the typical phenomena of molecular diffusion in liquids involve with, for example, liquid extraction or solvent extraction, and then we have diffusion of salt in blood. So as you know, because of the location or the position of the molecules in liquid is close from one to another, so therefore the diffusion characteristics is quite compact, and they have much more possibility to collide with each other. Okay, and of course the liquid diffusivity in liquid dependent on the concentration of diffusing solid. So this is accumular counter diffusion for the first case. Okay, we have the flux, okay, the mass flux, and then we have almost the same with the previous what you have learned in the gas or in the vapor. So you have the AB, then you have the concentration gradient here, or the mole fraction, and with the distance of diffusion. But there's one feature here, because of the concentration is not constant, so we have to introduce what we call as CAV, the average concentration. So it can be only be obtained by just divide the rho, the density, with the molecular weight of each respective position or points. Alright, move on to the next, which is diffusion of A through non-diffusing B. Okay, so this one is almost the same, except for the introduction of what we call as XB min, the mean value of XB. Okay, and you have to incorporate it with in the equation as well. So you have to consider C average as well. Okay, so this would be the example for this case number 2. So an ethanol A water B solution in the form of a stagnant film 2 mm thick at 293 K is in constant at one surface with organic solvent, which is ethanol. Okay, and is soluble and water is insoluble. So of course non-diffusing and B is 0 at 0.1. Concentration of ethanol is 16.88% and 0.2 6.88%, with the respective rho 1 and rho 2 at 972.8 and 988.1. So the diffusivity of ethanol is this value, and the mass is assumed as 100 kg. So let's just calculate the steady state of Na. Okay, so basically we have to govern this equation. Okay, and then the only problem is how to get the CAV and XBM, because we have been given the DAB, okay, this value, and XBM we will get XB when you get XA. So the task now is to determine what is XA at 0.1 and XA at 0.2. X is mole fraction, so we we have been given the mass fraction here. So that is why we have to assume the mass of solution as 100 kilogram. Then we will get the base of mass of 0.1 and 0.2, and then after that we will get the mole based on the volume value of molecular weight. Okay, so what we can do is that we just for ethanol we just divide at 0.2, just divide by the molecular weight of ethanol, and the rest is water, of course. So we'll divide with the molecular weight of water, and we will get the mole fraction of ethanol. Automatically we will get the mole fraction of water. It's 97.23%, and then with the same value, with the same approach, we get the mole fraction for ethanol at the first point. Okay, this time around it is not 6.8 anymore, it's 16.8. Okay, so and it will result in 0.07 and 0.92 or 934 for mole fraction of water. So from there we can get what you call as molecular weight at 0.2. Okay, because we have this value as a total mole, and then just divide 100 kilogram with the total mole and you will get the molecular weight. Then only then you can calculate for M1, then you get the C average at 50.6. Then you can compute XVM, and the value is 0.95. And once you get it, so you can easily get the value of Ne at 8.99 times 10 by power -7. Okay. So this will be the diffusion coefficient for the liquid for several types of solid. And then this is the way to calculate the diffusivity based on Stokes-Einstein equation and Wilkie-Chang equation, which is applicable for biological solids. And then we move on to the convective mass transfer and mass transfer coefficient. So this one is convective mass transfer coefficient. We know that the transfer rate is proportional to the transfer area times the driving force. So the exact equation is that you have mass transfer coefficient times transfer area times driving force. We know that driving force is the difference of concentration or concentration gradient. So we got this kind of equation for bulk with fluid concentration and also concentration near the surface, or I is referring to the interface. So Kc, the mass transfer coefficient for convective mass transfer coefficient. So it depends on the system geometry, fluid properties, and also fluid velocity. So this is one of the theory, which is boundary layer theory. Mass transfer often takes place in thin boundary layer, and we'll have to know that this region is supposed to be laminar in nature, but if it will be turbulent, so it cannot predict for Kc, so it's become problematic. So this is the delimitation of the boundary layer theory. The coefficient Kc depends on 2/3 power of diffusivity. So, and it decreases with increasing distance along the surface in the direction of flow. Okay, so this is what we call boundary layer theory. Okay. move on to the next one, which is interface mass transfer. Alright, so we have several modes of interface mass transfer, including the boundary layer theory just now. We have additional theory of two-film theory, penetration theory, and surface renewal theory. Okay, let's start with two-film theory. It is being governed or being developed by Nernst, Lewis, and Whitman in 1904. Initially, this two-film theory is originated from the film theory, which been governed by or being introduced by Nernst, and later on Lewis and Whitman got this two-film theory. Okay, two non-turbulent fictitious films are present on each other side of interface between the film. So it is basically two types of liquid and gas. They have their own interface, and at the center we have the interface of both phases. Okay, still governed by fixed law, two-film theory. Okay, and factor affecting a mass transfer of two miscible fluid phases is physical properties, concentration difference, and interfacial area, and also degree of turbulence. Okay, so this will be the assumption for this theory. It is steady state, should be laminar film, just like boundary layer theory, and sharp boundary, no transition. Okay, so this is will be one of the limitation, and no reaction and equilibrium exists at the interface, so no resistance whatsoever. So it is being simplified in theory, in nature. So next would be this what you call the derivation of the equation. So I would suggest you look at the documents from the island. Just download that two-film theory slide or PDF, and go through and make it yourself. So, or derive it yourself, and you will find that at the end of it, okay, you will find that this equation, okay, which happen to be the resistance of the mechanism, okay, or the mass transfer. Okay, if A is less soluble in liquid, H is very large, so of course the equation will be governed by this part. So this can be omitted. So the process become liquid phase control. Okay, so because we have KL, okay, and H is very big, and otherwise if it is very small, of course it will follow 1 over kg, so it is gas phase control. Okay, so mass transfer is directly proportional to molecular diffusivity of solid, into which is going it is going and inversely proportional to thickness of film. Okay, so this is another theory, penetration theory by Higby in 1935. So it considered unsteady state interface, so an improvement to the two-film theory. Okay, based on the fluid eddies, it is concentrated at the interface and being penetrate to the other phases. Okay, and this would be the equation that will govern the penetration theory. Okay, it's different compared to the previous one. And last but not least is surface renewal theory by Danckwerts, 1951. So just now, eddy current have their own time, similar time. This time it is being renewed every time, each and every time, and this would be the coefficient. Okay, the relationship of the coefficient. Right. So that's it for this video. Thank you very much.